Hello. Well, this will be pretty easy. There's actually nothing new in this section. Just got to go over all these weird shapes we learned about. Most of these don't actually roll off the tongue. Square, rectangle, yeah, use those words a lot. But the others, well, I kind of like what they laid out here. This is really pretty cool. It's a way to keep track of what the heck we just studied. What's this here? Well, this is just your standard old regular work-a-day, bring your lunch pail to work kind of quadrilateral. Nothing special. What about these here? Well, these four are all parallelograms, and they're a pretty important part of the quadrilateral family, I guess. So there are four of these parallelograms that are pretty important. This one here, this would be the rhombus. And so is this, because a square is a subset of a rhombus. Over here, we have a rectangle. A square is also falls into the rectangle definition. Why? Well, remember, a rectangle is just a parallelogram with four right angles. Well, a square is a parallelogram with four right angles. So it's a special type of rectangle. On the other hand, a rhombus is a quadrilateral with four congruent sides. Well, a square is a quadrilateral with four congruent sides. So it fits both of these definitions. In fact, if you have something that is both a rectangle and a rhombus, then it has to be a square. That part's kind of easy. This one over here, it's a parallelogram. We don't even have a special name for it. It's just a parallelogram. That's because we can't say that all the sides are congruent, and it doesn't have any 90-degree angles. It's just a parallelogram. So I like this diagram because it shows the subheadings. We got quadrilateral. Below that we got parallelogram. In that category we've got rectangle and rhombus. And in those two categories we have one that fits both, and that's a square. Over here, well, these are both trapezoids. The only difference is we have a trapezoid and an isosceles trapezoid, and there's your subset down here. So trapezoids, it's kind of easier to remember all of those. There's trapezoids, and then there's isosceles trapezoids, and that's about it. Kites? No, they're even easier. There's kites, and then there's kites. And that's it. Doesn't go any farther than that, just kites. And remember, the kite is the one that has two adjacent sides are congruent. Whereas with a parallelogram, opposite sides are congruent. So, yeah, a kite's kind of like taking a parallelogram and switching things around, except that, notice that a parallelogram with two opposite sides congruent, you end up with all kinds of possibilities. You could make rectangles, rhombuses, squares. When you change that and say, well, the two consecutive sides are now congruent, you only end up with one. It doesn't have any subsets down here. No, that was an extraneous mark, sorry. Well, this is cool for remembering, sticking in your head how to separate these all out. So these are the main types of quadrilaterals: the plain old ordinary quadrilateral, the four parallelograms, the two different trapezoids, and the one kite. And if you're trying to remember all the parallelograms, trapezoids, and kites, and get confused, just remember it's 1 for a kite, double it, and you get 2 different trapezoids. Double that, and there are 4 types of parallelograms. A plain old parallelogram, and then rectangle, square, and rhombus. Now that's pretty simple. Now we're just going to work some problems to help us remember the difference between all these different quadrilaterals. Won't be too tough. Now here's a very instructive problem, I think, in terms of helping you remember what's what. Just going to go through these, and we're going to put x's in every property that applies. For instance, all sides are congruent. Rectangle? No, opposite sides are congruent. Rhombus? Yeah, that works. Excuse me, a check mark would make more sense. Yeah, let's be rebellious and use check marks instead. All sides are congruent in a square. Oh, that's true. And they always have to have this property. For instance, a kite could have all congruent sides, but that's not the definition. The definition is that consecutive sides are congruent, so this is no good. Trapezoid? Definitely not. Both pairs of opposite sides are congruent. Well, I'd say that's a rectangle for sure. Well, if a rhombus has all sides congruent, then the opposite sides must be a square. Same thing. If all the sides are congruent, then the opposite sides are congruent. Kite? No. The consecutive sides are congruent. Trapezoid? An isosceles trapezoid could have 1 pair, but that's an isosceles trapezoid. In general, a trapezoid doesn't have to have any congruent pairs. So it's just these 3. Both pairs of opposite sides are parallel. Well, that is the definition of a parallelogram. So, how many of these are parallel? Jeepers. Someday I'm going to learn how to talk without sounding like I have a mouthful of rocks. Parallelograms have both pairs of opposite sides parallel. So, a rectangle's a parallelogram. A rhombus? Yes. A square? Yes. Kite? No. Trapezoid? No. Exactly 1 pair of opposite sides are parallel. Well, that's true for a trapezoid. Exactly 1 pair. By that I think they mean only 1 pair. I don't think that's true for any of these others. So, trapezoid is the only one which has this property. And this one says all angles are congruent. Well, that would be true for a rectangle because they're all 90 degrees. Would be true for a square because they're all 90 degrees. Kite? No. There's 1 pair of congruent angles in a kite. In a trapezoid, we could have 2 base pairs in an isosceles triangle. Otherwise, we might not have any congruent angles. Rhombus? Again, we have opposite pairs of congruent angles, but they're not all congruent, so it looks to me like it's just the rectangle and the square. Exactly 1 pair of opposite angles are congruent. Well, that applied to the kite for sure. The square? No, both pairs. The rhombus? Both pairs. A rectangle, trapezoid, pretty sure Kite, or pardon me, Kite is the only one that's going to exhibit this property. Exactly one pair. Diagonals are perpendicular. Well, let's see here. That's true for a kite, wasn't it? It's true for a square. And a square is a special case of a rhombus, although that's not. And I probably should have done it the other way. A rhombus has perpendicular diagonals. A square, being a special case of a rhombus, would also have perpendicular diagonals. And a kite, well, it has perpendicular diagonals just because we already showed why it's true that they're perpendicular. So it's just those three. Diagonals are congruent. Now let's see, that's true for a rectangle. I don't think it's true for a rhombus. Remember, rhombus is kind of a lopsided square. So you end up stretching out one diagonal and shrinking the other. Is it true for a kite? No. And I think we saw problems in the last section that showed that diagonals for an ordinary trapezoid are definitely not congruent, only for an isosceles trapezoid. So we've got the square and the rectangle, and those are the two with congruent diagonals. And diagonals bisect each other. Well, let's see here. That works for a rectangle. It works for a rhombus. And if it's true for a rhombus, it must be true for a square. Now for the kite, no, they don't have to. Trapezoid, same thing. These two do not have to bisect each other. This little chart here, and it's probably worth having a copy of this to study for the standardized exam, because you'll need to know these things. Well, looks like inseam and flea bite are at it again. They just can't get anything right. They say that angle B and C are supplements, so AB is parallel to CD. I think what they're saying is that ABDC is okay. They're saying that because these two are supplementary, they have a parallelogram. Well, all the consecutive angles in a parallelogram are supplementary. These two are, I think. Let's see here. Yeah, they add up to 180. But these two, they don't. And these are also consecutive angles. So all the consecutive angle pairs have to be supplementary, not just find one pair and then boom, it's a parallelogram. It's not that easy. They all have to. If you're going to use the supplementary property, you have to show that it applies to all consecutive or adjacent angles. And here they want to know, based on this, what kind of a quadrilateral do we have? Well, these two are parallel. These are congruent. And these two lines so we have a pair of opposite sides, which are congruent, and a pair of parallel. Now, a pair of parallel sides. Now, that could fit an isosceles trapezoid, except that these are 90-degree angles. If it was like this, if that were the line, and then it was like that, well, and then these two, heck, that would be an isosceles trapezoid because we know that this top and bottom are parallel. However, we have 90-degree angles here, so we can say even more. We have a parallelogram. Opposite sides are congruent. One pair of opposite sides is congruent and the other pair is parallel. That gives us a parallelogram, but we have a 90-degree angle, which gives us a rectangle. Could it be a square? Yes. Square wasn't one of the choices. And we don't know that these sides are congruent to these sides. It's certainly not drawn to look like it is, but we can't assume from the drawing that everything is at scale. So if they had given us information about congruence of these two sides, or pardon me, of this side and this side, then we'd know that we had a square, but we don't. So we'll settle for a rectangle. It could be an isosceles trapezoid if we had it like that, but normally you wouldn't call this an isosceles trapezoid because of the right angles, and because these two congruent sides and these parallel sides combined with the 90-degree angles mean that we have a parallelogram, and more than that, we have a rectangle. So what is a quadrilateral with congruent diagonals and exactly one pair of congruent sides? Well, congruent diagonals, that could be rectangle, square, or isosceles trapezoid. Only one pair of congruent sides? Well, in isosceles trapezoid, we have exactly one pair of congruent sides. These sides are not congruent. So, you should have drawn an isosceles trapezoid. Pretty easy. Here we're given points. We're asked to graph these points, connect the dots, and form a quadrilateral. And the question is, exactly what kind of quadrilateral do we have here? Well, I would say it looks like an isosceles isosceles trapezoid. Is it a trapezoid? Well, let's see here. Y coordinate here is 8, y coordinate here is 8. That means this is horizontal. Y coordinate's 1, y coordinate's 1. This is horizontal, so we have these two opposite sides are parallel. Okay. Now, if these two sides were equal, we would definitely have... Oh, and there's one other thing we could take a look at, which is also real simple. The length of this goes from 3 to 5. That's 2. The length of this goes from 2 to 6. That's 4. So these are definitely parallel opposite sides and not congruent. Now these sides here, they certainly look congruent. But how do we check? Well, we check the diagonals. If the diagonals turn out to be congruent, then we have an isosceles trapezoid, or a rectangle or a square. But this is not a rectangle or a square. We could easily show that we don't have 90-degree angles here. What's the length of this? And this time we're going to do it the easy way, because we don't need an actual answer for the length. We just have to know if they're the same. So what's delta y here? It goes from 1 to 8. That's 7 squared. That's 49. And that's true for both. But let's go from R to P first, okay? So we have RP. And delta y is 7, so that's 7 squared is 49. What about delta x? It goes from 5 to 2. That's a difference of 3. And 3 squared is 9. Before I work this all out, it's going to be really easy to tell whether I'm right or not to see if I get the same thing. Delta y is the same for both because these lines are parallel. So the first term is going to be 49. Now, for SQ, what's our delta x? We went from 3 to 6. 6 minus 3 is 3. We're done. The diagonals are congruent. They have equal lengths, so they're congruent. So we have an isosceles trapezoid. If you want to know what this is, go ahead and punch it into your calculator, but it's irrelevant. What matters is these two are the same. If they're equal, then in this particular case, we know we have an isosceles trapezoid. Now this one's kind of looks kind of tough. Might not be that bad. They're asking us to draw these bisectors for each angle in the rectangle. So here's a bisector, here's a bisector. Remember, the diagonals in a rectangle are not bisectors. They don't bisect the angles. A diagonal that went from this corner to this corner would not bisect the angles. That's why these things are not diagonals. Well, we've produced something in the middle here. It's got 4 sides. But what would this be? And don't go by what it looks like, because it's not necessarily drawn correctly. Partly because that would be cheating, and partly because I don't draw very well. Well, what do we know about what's going on here? After all, one of the things we can figure out, or might want to figure out in determining what we have here, is work out the angles in here. If we can say something about the angles inside, we might know something about this quadrilateral. And angles are about all we do know about, because this is no particular size rectangle. We don't know anything about the lengths of these bisectors. But this is a 90-degree angle right here. We know that because it's a rectangle. That means this is 45 degrees. And this is 45 degrees because this is a bisector. So it's 45 and this is 45. That means this is a right angle. Well, that's interesting. Well, that tells us that this is a right angle. Remember, these are a pair of vertical angles, so they're congruent. If this is a right angle, this must be a right angle. Over here, same thing. This is 45. Well, maybe I should have done this one first. This is 45 here. And this is 45. So this is 90. And that means this is 90. Okay. But if this is 45, and this angle here, actually, we don't have to worry about these others. All the way around is 360. Here we have two angles that are 90. That's 180. So there's 180 degrees left over, and pardon me, I'm getting kind of dumb here. We don't even need to know that these are right angles. We know this is a right angle because this is the right angle and these are supplementary. What we need to know about is these two here. Are these right angles or not? Well, this one we can go the other way. We know this is 90 and this is 45. So this angle here must be 45. So this is This is 45 degrees. And I would like to be able to say that from symmetry, we know that this interior angle is 45 degrees also, but yeah, it's kind of hard to prove. In the same way, we can show that this one over here, well, I have to show, it just obviously is, it's a bisector. This has to be 90 also, because this is 90 and this is a straight line here. That means this angle over here is also 45. So we got this angle and this angle are 45. This is 90 degrees, but if this angle is 45 and this angle is 45, then this one must be 90. And that means this one is 90. And now I think we're done because we've got 3 90-degree angles. 4 of them have to add up to 360. So this one is also a right angle. So now we know we got 4 right angles. We definitely have a quadrilateral, which means we have a rectangle or a square. We know that this side is congruent to this side. In other words, we know this much already. Now, if we think we have a square, we're going to have to show that consecutive sides are also congruent. These are all 90 degrees, so consecutive sides, we're not trying to prove it's a kite. We know that opposite sides are congruent. Now, if we can show that the consecutive sides are congruent to the opposite sides, that means all 4 sides are congruent. Well, what do we got here? We've got a 45-45 triangle here and another one here. This is 45. This is 90. So this over here must be 45. That's this angle here. So that's our 45-45, 90. This triangle and this triangle share a side. So we have angle, side, angle. Although for a right triangle, you just angle side is good enough. This side is congruent to itself. That's how we know that this triangle is congruent to this triangle. Well, what about these? This triangle here. In other words, and this one compared to this one. Well, they share a side, don't they? It's congruent to itself. They're 90-degree angles. Pardon me. They're right angles. So we've got our angle, side, angle, and this triangle here is congruent to this triangle. I'm going to give these names. We'll call this triangle A. This is triangle B, and this is triangle C. Now, if A was congruent to C, then we could just match up the corresponding parts. And these sides that are forming the parallelogram are the corresponding parts. So if it turns out that C is congruent to A, then we can show that these consecutive sides are congruent, and we're done. Well, we just showed that A is congruent to B, and then B is congruent to C. So, by transitivity, A is congruent to C. And we match up corresponding parts of congruent triangles, and they're congruent. So once again, the way to get to the solution was to break up the polygon into congruent triangles, like we did here. We've got A, that's this one here, and then B, which is this one. They share a side, and that's the key to showing the congruence. And then B and C, they share a side, and that's the key to showing that they're congruent. Not every triangle that shares a side with another triangle is congruent to it, but you can use the fact that the side is congruent to itself, combine that with congruent angles, and then you can show congruence. So these two sides are congruent, and what we really have in the middle here is a square. And you might have guessed that just from symmetry. I mean, what's the difference if we bisect this angle and then bisect this angle? It seems like these lines are all, there's a symmetry going on here, where you would expect that once they started intersecting, they would produce segments that were all the same length. That's just, intuitively you might have guessed that. It wouldn't surprise me at all. But to prove it, you use congruent triangles once again. Well, here we're given that AC and BD bisect each other. They're congruent and not perpendicular. So I went ahead and drew that down here. Here's AC, here's BD. They're congruent and not perpendicular. Now if we fill these in here, what kind of a quadrilateral are we going to get? Well, I drew this very badly, but it shouldn't matter because we need to classify this according to its diagonals. So for congruent diagonals, what do we have? It could be a rectangle, RE period, a square, congruent. Well, an isosceles trapezoid would work. So, rectangle, square, isosceles trapezoid. I think those are our choices. However, although the diagonals in isosceles triangle are congruent, they don't bisect each other, do they? No. I mean, it's easy to see why they wouldn't. Draw a simple little trapezoid. Trapezoid. Heck, it looks more like a mesa in the southwest, doesn't it? Anyway, as we draw these, well, I think it's pretty easy to see that that's not a midpoint, so we can forget that. That means we've got a rectangle or a square. But remember, in a square, just like a rhombus, the diagonals are going to be perpendicular. So what we're left with is rectangle. It couldn't be an isosceles trapezoid because they bisect each other. It couldn't be a square because they're not perpendicular. Rectangle is the only one left over, and that works. Kind of looks like a rectangle to me. Well, in the second case, they asked us to draw diagonals which are perpendicular but not congruent. The question is, what do we end up with? Well, what can it be? Diagonals are perpendicular. That means square, rhombus, or kite. Now, for a square, the diagonals are congruent. So we can cross that out. That means we have a rhombus or a kite. But we still have that they bisect each other. The diagonals of a rhombus bisect, but a kite, no. Diagonals of a kite do not. Notice I didn't draw this very well. You can't tell what the heck this is. In fact, it looks a lot like a kite, but the fact is it's actually a rhombus. Well, that's about it.